Hello, my name is Arturo Kohatsu-Higa, and I would like to present to you some joint work that I have developed with Dan Crisan at Imperial College, which is related with a topic that we might call derivatives of skill diffusions, which I will try to explain to you a little bit more in detail. First, I will try to explain to you a little bit the historical background and two other results, one of them from the theoretical side that might relate to our motivation for our current research, and another one which is an application. So let's start first with the historical background. The historical background is given by this formula here, which is the classical formula for the derivative of flows, which applies to smooth diffusion where the coefficients are smooth. And then we can actually differentiate the process X, and the derivative, which is denoted here as dxt, is actually the solution of a linear equation, which is the linear equation that appears here, which is obtained through a differentiation of the classical formula. I have also written a consequence of this result, which is written here, which uses in particular the expectation, which is really not necessary in the case of smooth diffusions because the derivatives can be computed pathwise. But for the case that we will be dealing with, we will see that these expectations will be necessary here. So there are many extensions of this result. In particular, I want to discuss one of them, which is related with reflected processes. And in particular, I will explain to you in a very simple term the result of Andres. And there are many other people who have worked on this problem. And here are some of the references. All the references appear in the articles that I will mention later. So let's start by here setting G a domain with a smooth boundary. So this is the setup of the article of Andres. Our setup will change a little bit of notation, but I just copied the result of Andres as it appears in the paper. So he starts by considering now the process, which has a diffusion coefficient, which is the identity constant, and then a drift B, and he considers this process to be reflected. In other words, and here there's a picture that more or less explains what a reflected process is. A process is reflected if this is the domain G, it means that the process starts at X and it starts running until it hits the boundary, and then at the boundary is contained by this regulator process L in the direction of the normal. So the process will be always pushed in the minimal way possible, and that minimal way is explained in these two equations here, only when the process is at the boundary, so that the final result is always in G. So this is the reflected process, and the question that many of these authors answer is what is the derivative of xt with respect to x? And the main reason why one can differentiate this process is because the local time is a Lipschitz application, and therefore, because of a Lipschitz application, you can exploit these properties in order to obtain its differentiability. And the derivative is quoted in this theorem, the theorem 2.1. And the derivative essentially has two parts. So the first part, which is what one might expect, is just the usual derivative. Here there are partial derivatives, and that's why there is a nu here, which is the direction of the derivative. And then as before, you are just differentiating inside the integrals, and because the diffusion coefficient is the constant, the derivative is 0. But this is only valid before you touch the boundary. So this set MC in that paper means this is the first time you touch the boundary. After you have touched the boundary, the derivative changed a little bit its form, and is of this form, and I will try to explain what this means. So you have the process that started at X and it was reflected at the boundary like before. And let's suppose that you want to compute the derivative of time t. Therefore, you have to start looking at the last time you touch the boundary. And then from that last time that you touch the boundary up to the time t, you need to follow this evolution. But at the time rt, what happens is that there is a projection operator this is a operator that projects all the columns of the matrix eta, because now eta is a matrix, and so it projects all the columns into the tangent space. Therefore, these matrix here, their columns always belong to the tangent space, and therefore one might say that the components that are orthogonal to the boundary are zero. Now, the reason for this can be explained very simply, and it's actually also good to understand it in the one-dimensional case. In the one-dimensional case, when you have reflected Brownian motion, what happens is that, again, if you differentiate the Brownian motion because you haven't touched the boundary in this piece, then the derivative is 1, because as you change x, then the Brownian motion will move parallel. But as soon as you have touched the boundary, after the boundary, then the derivative is 0. And this is due to the Markov property. Essentially, it means that after tau, the reflected Brownian motion doesn't know where it came from, and therefore the derivative of this process is the indicator. And so this indicator actually has some flavor of a kill process. So this is a process that is killed as soon as you touch the boundary. So one of the motivations for our research was to say, okay, what would be the derivative of the kill process? Another reason for our research was given by an application which is given by Costantini, Gobet, and El-Karoui, which is a method in order to compute optimal boundaries for optimal stopping problems. So essentially, there is an assumption that the optimal domain has to be regular. And what they obtain here is this result here, which I will not explain in full detail. I will refer to you to the paper, and I will just explain the basics so that you understand our motivation. So what happens here is that you have domain D that you want to approximate by using an approximative domain d epsilon. So the parameter of approximation here is epsilon. And in order to be able to use a gradient descent method, what you want to compute is you want to compute the optimal value function as a function of epsilon, and you want to differentiate it with respect to epsilon. And the derivative has an explicit form, which is given in that paper, which is this one here. The random variable here, theta, the function theta and the function g are given, and the function c also. But what needs to be computed is the gradient of u. The gradient of u is, again, the solution itself, and it has to be evaluated at the boundary. So this tau is the first time you reach the boundary. And therefore, what you need to do in order to be able to use this formula to achieve a gradient descent method is to be able to compute the gradient of the function u at the boundary. And so this is another motivation for our research, although we'll start from one dimension going towards the multidimensional case, and therefore, our progress in this problem will go slowly. So what we are going to do is we are going to try to establish the following representation. So we have here the derivative of the kill process. This is called the kill process because as soon as you touch the boundary, this indicator becomes 0, and therefore the process can take like a cemetery value. And what we want is to obtain a formula of this type. And if you recall what I just said before, I want to remark to you that here I'm writing yt and not xt like in the classical formulation. And so if you recall again, in this formula, in the classical formula, we have xt and xt here. Now we are going to have this xt and xt will not be the same. This one will be different, but they will be not so different. In particular, this will be the diffusion process, and this one here will be the reflected version of it. Now, so we want to obtain certain formulas, and psi t will be the derivative in such a way that they are dynamic. Dynamic in the sense that they have to be very similar to the equations that we obtain in the classical cases, and in some sense, well, they have to be valid, of course, for all times t. So let me just then state what we have already finished at the papers that you can find on the web. And so we have divided our study in steps because we have found that the arguments that we need to do in order to obtain these results could be complicated. And so we decided to divide the study in two stages. The first stage will deal only with the one-dimensional case. And in the one-dimensional case, what we'll have is that reflected processes will appear. So this was the process Y that I was talking about before. And therefore, local times will start to appear. And so the main issue in this article is how these local times will appear in the whole proof. In the multidimensional case in particular, we'll consider the simplest case possible, which is the half-space case, and we will assume that there is no correlation at the boundary. So you can think that what we are assuming here is that the diffusion coefficient is the identity at the boundary. And what will happen in this situation is that there will be the appearance of jumps for the derivative process, and therefore this is different from the one-dimensional case, and therefore the whole proof has important changes in order to deal with this new feature. And so again, here in this presentation, I will only try to explain the results and the main ideas, but I will not give details about the proofs, which can be found in these two papers. Now, the first thing that I would like to explain to you is why we have a reflection in these formulas. And I will start with a one-dimensional example of Brownian motion without drift. And it's very important for you to understand that this is a case without drift. So what we need to prove is exactly this formula here. And we will assume this is what is called a boundary condition. And in this particular case, when we have only Brownian motion, actually this formula can be written very explicitly and analytically, because here it will be the density. This is Kiel-Brownian motion, and so the density of Kiel-Brownian motion is written here and is denoted by Qt minus. So this is the derivative, and the only thing that I have written is that I have written the expectation as an integral where the domain goes from L to infinity. On the other hand, I have f prime, and instead of writing it this way, I have written the integrated by parts version, which is having fy here, and here the derivative of what I call qt plus, which is the density of the reflected process. Of course, here I'm assuming that my derivative process is probably 1, and therefore that's why I only have the derivative of the reflected process. Now, the question is now how you prove this identity. Well, actually, as I said before, in the particular case of Brownian motion, these Qt minus and Qt plus can be explicitly written by using the reflection principle, and they are written here, and they are nothing else than the Gaussian density, which counts all the paths that start from X and arrive at Y, and you take away, in the case of Kiel processes, all the paths that have crossed the boundary. On the other hand, for reflection, you have to add all these paths because the ones that cross the boundary actually get reflected and can end up in Y. So this sort of symmetry that appears here gives you the following property that you can check just by direct differentiation, which might be called a symmetry property. And this symmetry property is only valid for Brownian motion. As soon as you add a drift, as soon as your coefficients are not constant, this property is lost. But anyway, for Brownian motion, we have it. And because we have this property, now you can put the derivative of x here. You use the symmetry property, you obtain this derivative, you do integration by parts, and you obtain the final formula, which gives you this result and which explains to you why Brownian motion has as an expression on the other side reflected Brownian motion. But on the other hand, although this argument is analytical, doesn't explain to you, probabilistically speaking, what is going on. It doesn't also help you to try to extend this proof to a general situation. And so it's very difficult to apply. And what we will see next is a different type of argument, which of course is a different way of writing the same argument, but which is the argument that will be generalized in the proofs of our articles. What we need to do is to consider the probability of crossing the boundary. The probability of crossing the boundary can be computed and has this form. It's an exponential. And then what you are going to do is you are going to take the expectation of the kill process and you are going to condition the indicator with respect to xt. So this will be 1 minus the probability that you cross the boundary. And now you can differentiate this process. And you have two terms. The first term is f prime and then the probability that you will not cross the boundary. And then you have, because a minus here, you have minus the derivative of the probability of crossing the boundary. Then what you do now is you do an integration by parts of this formula in order to obtain this expression, which now has f prime. And then you realize that this measure here, or 1 plus pt xx xt, corresponds to the process that is reflected. So for that reason, I call this m bar t, like if it were a change of measure. And then you realize that under this m bar t, what you have is a reflected process, and your derivative process et is 1. So here, of course, as I explained previously, you have used the integration by parts formula in order to pass from this derivative into f, and therefore you need some sort of elliptic condition in order to be able to do this formula. So now this argument can be extended by using approximations. So in short time intervals, you could use this argument. And then you might wonder if actually this can be done in continuous time by defining this measure m bar of t continuously. But this is impossible because we all know that we cannot change Brownian motion into a reflected Brownian motion just by a change of measure. And so that's one of the important reasons why we have to resort to approximations in order to do this argument. The only parts of this argument that will work when you are doing the full case scenario and the approximation are these two, the first one and the last one, and you will be taking limits in these formulas. And because you are going to take limits, of course, then you have approximations, and then you need to apply Arcela-Ascoli argument. Okay, so let me just say something that I will not repeat again later, but these formulas actually will have limits when you take the initial points at the boundary, which is, as I explained previously, very important for certain applications. And the general result in what I call the symmetric case, when you don't have a drift, is as follows, is given by the reflected process here, which is reflected by this regulator process, which I call BT. And what is going to happen is that the approximations will give you these processes here. And you see this is the delta IZ, which I call now the increments of the new Brownian motion under the change of measure m bar. And so what happens here is that now we have to prove that these processes converge to this one. And so in this case, it's not so difficult because there are no local times involved. But we will see later that this will become important. Still, you have to prove the convergence of these terms here to these local times. Anyway, so now what happens with the case with drift? The case with drift, which we'll consider in here, let's suppose that xt is x plus bt plus sigma wt, and now I have a, I will denote a by sigma squared. And the first idea is fairly simple. What you have to do is first you apply Girsanov transformation. So I apply Girsanov transformation, and I would like to take this whole function here as a function of x. In order to do that, I will need to change my wt and convert it into x. And in order to do that, it's very simple. You just have to use the equation itself. So if you do that, you obtain that kt yx is given by this. And so you have to remark now that this is a function of xt and it's a function of x. So when you differentiate this, you will have to differentiate this whole thing as a function of xt, but also as a function of x. So this will give you, in fact, the following three terms. The first one is the derivative of f, which has kt. The second one, f is not differentiated, but k has to be differentiated, and that's why you obtain ba minus 1, which is this one here. And there is an extra term which requires the differentiation of this minus x, and that's why you have a minus, but this indicator remains here. And so now you see that you have here f and you have here f, and what happens is that you have a tau in the middle here, and so it's not so easy to take the integration by parts like we did before. And in fact, this is part of the difficult problem that arises in the case with drift. And this is natural that it appears because when you consider Brownian motion plus drift, the reflection principle is not valid and the interactions of the Brownian motion with the boundary will become important. In fact, I can show you already one situation where this is important if you start to analyze this kt, y, t, x. Previously, here, this was the Girsanov transformation. Now, once you have differentiated, now you have yt here, which means that if I want to rewrite this by using Brownian motion in order to change it back by using the Girsanov, you see that you obtain two terms. Because yt is reflected Brownian motion, you obtain your Brownian motion here, but you also obtain the regulator process here. So you will be using this part in order to gain back your drift, but the derivative is no longer going to be one probable because you have this extra term. And actually, dealing with this extra term here is the difficult part of the problem. And just to explain some ideas of how we deal with this, first you change xt's into y's, because here, as long as you haven't touched the boundary, I can change x by y, is exactly the same. And then you have obtained this formula here. And then somehow, what you have to do is you have to do a conditional argument where I condition this f of yt to the first time that you touch the boundary. Okay, I have written this in red because actually you cannot do this either in continuous time. You have to do it in discrete time because this filtration doesn't make any sense. But anyway, the underlying idea is that you consider again something like this, where f at the boundary is 0, and therefore now this is again a derivative, and this derivative generates a linear equation. This linear equation gives you the final answer, which is going to be this one here. Okay, so this final answer here, which is going to be that the derivative of Brownian motion plus drift is not 1, but this is the exponential of 2b divided by a multiplied by the regulator process of t. This is something that has also been realized in other contexts, which are not necessarily the same as this one, which is in some articles where there is a relation, the authors find a relation between optimal stopping and singular control in the constant case scenario. So for us, this is just a starting point, and what we want to do is to extend this result actually to the non-constant case. And this is what we do in the paper. And the result is this one here. Again, as I said before, one of the big parts is here to study the local times, which will appear now also in the derivative process, not only in the underlying process Bt. And so obtaining these limits is not so easy. And that's why we divided the study in two parts. So here we are only going to obtain this local time here. And we need to prove the equicontinuity of the approximating first derivatives. All right, so now let me go into the half-space situation and let me try to explain you, as I said at the beginning, how jumps appear in this case. In order to do that, I will consider a very simple scenario, which is a two-dimensional situation where the two components are independent. So you have W1 and W2, they are independent. And of course, the stopping time or the exit time will be only related with the first component, so it's related to W1 and therefore is independent of W2. And therefore, the formula for the derivative is very easy to obtain. I will obtain the derivative with respect to x1 first. The derivative with respect to x1 can be obtained by conditioning with respect to x2 because W2 is independent of W1. And so you will obtain the classical result, which is going to be the reflection multiplied by 1, which is the previous one-dimensional result. On the other hand, when you do the derivative with respect to x2, what happens is that now you are going to condition to all the first noise, and the second one doesn't depend on the exit time. And therefore, the derivative of this is just 1, but the indicator that you have here will remain. But this indicator can be evaluated on x, or the reflected process is the same. And so you obtain that the derivative in the second direction is the indicator of tau of y greater than t. Now, if you start looking at this dynamically, as I was trying to explain before, what happens when the time t evolves, changes? So you see that in the first component is always 1. So in the normal direction, the direction E1, this column is going to be always 1. In the other direction, which is, you could call the tangential direction because it's E2, you see that it will be 1 until the first time you touch the boundary. After that, it will become 0. So if you recall what I explained to you about the reflecting case, it's dual. It's completely the reverse situation. In the reflected case, this one is 1 and this one becomes 0 when you touch the boundary. Now, the result is written this way. I'm not going to try to go over much of the notation here, but I just want to remark that the form of the derivatives are like before, like in the classical smooth case, except that you obtain a number of local terms. The first local term, which appears here, comes from the interaction between the drift and the boundary. Here I have not written A because it's just a renormalization of the regulator process, but you can see here that this E1 transpose, this is the one that talks to you about the jumps. Okay, so in the direction E2 will become 0, and this rho t is nothing else than the RT that was described in the reflected case. So the situation is very similar, like before, in the sense that the process will have the same derivatives that you usually have. Every time you touch a boundary, there is a jump, and this jump makes 0 the tangential columns of E, and in the other directions it becomes reflections, like in the one-dimensional case. So let me now conclude with what we have tried to explain here in these two papers. And the first main result is that we have provided a framework to obtain dynamic versions of the derivative for Kiel diffusion process. So as I explained previously, this argument, which is complicated, has 2 steps. One, how to obtain the limits so that you obtain the local times, and the second, how to obtain the jump times. The probabilistic representation, as we have said, requires the use of a reflected process. The local time, which appears in the derivative, only appears due to the interaction between the drift and the boundary. Okay? When there is no drift, the derivative process doesn't have a local time term. In the multidimensional case, we see that jumps appears. And here I remark again that an argument with partial differential equations will be not so easy to obtain, because it will mean that from a Dirichlet problem, somehow you have to generate non-local terms in your final equation, because the derivative equation has this non-local character which comes from the jumps. And so, as I also said before, the difficulty of the technique using the proof is due to the approximating procedure. In the one-dimensional situation, there are particular cases, sub-cases, where you can do the proof in a much simpler way, for example, by using Lamperti transformation, but then it becomes clear that this argument cannot be carried out to multi-dimensions, and therefore that's why in this series of papers we wanted to present the general technique that will allow you to obtain various numbers of results. And so something that is very important is that the way the proof of differentiability is done in this killing situation and the way the jumps are obtained are actually completely different from the reflected case. The arguments are completely different because in the reflected case, you use a lot the differentiability of the local time or the ellipsis property of the local time, which in this case, at least at the beginning, when you have the exit time tau, this is not given here. Although I have not discussed this in this presentation, you can see in the paper that we have obtained also some Bismut-Elworthy formulas, which are based on the last excursion from the boundary. So this implies that you can apply these formulas again at the boundary. Some other formulas which are available right now do not allow you to take as initial point a boundary point. And this is remarked in the introduction of our articles. So now let me just finish with some future work. We are currently developing the result, and we believe that a result more or less of this type has to be true in the multidimensional situation when you have smooth domains. And this proof is actually becoming extremely demanding and long for many reasons, but let me just explain some of them. When you have a smooth domain, of course, you have to divide the domain in charts, and you have to define approximations on those charts. And so when you do that, you have to be very careful in order to define the approximation in such a way that the approximation will not cross two different charts too many times in one small time interval. If that happens, it's very difficult to control the approximation procedure and obtain limits. The Girsanov argument also becomes extremely difficult because the Girsanov theorem does not preserve very good properties of the charts, and therefore this also requires new arguments that were not available in the half space situation. But what you can see on the other hand is that in the results, of course, the curvature should appear, and then the reflection of the process has to be oblique. Okay. Another application that we have been developing and we are still working is the differentiation of the stopping time, and we believe a result of this type should be true, but of course we are still on the way of proving it. A remark is that our formulas actually probably satisfy this generalized formula in the sense that they don't have to be functions of the terminal time, but it could be some function of the path. For example, if you consider an integral of x, the same derivative formulas are true, which actually point out on the possibility of obtaining a certain weak uniqueness for the derivative process. And from there, which implies, of course, that the processes are Markov, then we can find finally a relation to the Feynman-Kac formula, which is, as I described previously, it will have to have certain non-local terms, which we think are not trivial at all. In the two papers are also other applications which I have not mentioned in this presentation, and then I finish with some of the main references. In the articles, you will find more detailed references, and please do not hesitate to contact us if you have an interest on any of the issues that I have discussed in this presentation. So thank you for your attention,